So I put a title on this of Houston, we have a problem. For those below a certain age, that might not give you the same feeling in your stomach. But actually, I put this up because my experience of actually dealing with automotive security problems and all this sort of stuff is that feeling in the pit of your stomach when it's gone horribly wrong, something's blown out the side of it, and your capsule is heading away from where you want it to be, not towards where you wanted it to be. And the question in relation to this is somewhat to do with, so how many of the design things were actually instrumental in getting you back in relation to that? So for those of you who don't know, we blew out the side of the capsule, we flew around the moon and came back and managed to manually get it back into the Earth's atmosphere. There are good films about it, I understand. And on my first slide here, there are some articles that we've done around this sort of stuff. So they're actually looking at not the chip stuff, not the bits that we're talking about at the bottom end, the things that really matter to me, obviously, but actually I've had a crash with my autonomous driving system. What caused it? It was the AI system that caused this. How do I get data? What do I do around those? Where do I get evidence from around those sort of stuff? How does my CISO know anything about safety and how those things work? And asking those sorts of questions. So those are the sorts of things that we've been trying to ask. We have a number of formulae and things that we put up there. So this is more text than you normally get from the rest of the speakers put together. But these are actually trying to say, actually, when it comes to doing security across complex systems, putting these things together, our challenge as engineers is actually that we've known about this stuff. We've known about it since the 19th century. We did all the maths on that. We did all the maths on computer science in the first half of the 20th century. And then somehow, magically, as we got into the 21st century, we waved our arms and pretended there was some other solution that didn't work on the same fundamentals. And it's just not true. And the courts are going to call us out on this. So these elements about determinism, deterministic, these elements about single-bit errors. So we talk about digital security by design, but in a car, interestingly, the bit I get prosecuted for is the fact I rammed into somebody with my tons of steel. They have no interest in the fact that I thought it didn't crash. They are interested in the fact that we banged into people. And as we do more and more significant things, and that is what we're doing, more and more significant things, I agree with exactly this trajectory. What we're getting to is a situation where these things will be prosecuted, and they will be prosecuted in court. Witness for the prosecution here. If you look at the automotive industry, what you're seeing is a 40% per annum increase in the number of recalls based on complexity. We don't know how to handle these things, 40% per annum, and this is now the #1 recall. And if you put the second thing up there that I don't have, that means you're looking at in the order of 250,000 potentially safety-critical cybersecurity incidents in an 8-year life of a vehicle. And we don't know how to do this. So the real question in relation to digital security by design is, what tools have we got that would allow us to do digital security by design for an emergent property, i.e. a property that we knew nothing about when we designed these systems? Because that is what the value of the economy, that is what the vehicles we're now doing are all dependent on. And we have to answer those sorts of questions. This is what we set out in ASIN to put together. We set out to put together a methodology that was capable of being tested in a court. We didn't go, can I prove it to the security professionals? We figured that when it goes wrong, I'm going to be prosecuted. And our observation was the methodology that we as engineers do and what I'm going to be asked about when I get to court aren't the same. And they were designed around much smaller electromechanical systems. So on this stuff that we were talking about on AI, for instance, one of the really interesting questions is, how does that work? What are you going to say when you're standing up there? Because I intend to be the expert witness. Second thing is for operators, what have you got to generate? What does this digital security by design look like? You know, what are the questions there? And the third thing is, everybody must agree on the evidence. And I'm pretty sure it doesn't involve waving your arms and saying, I thought it was a bit better. So we've got to get back to doing engineering around these things. So part of the observation here is, this is a fundamental move. We are doing our design in operational space, not in design space. These things are changing what they do. And that's at a really rapid pace. And we tried to put together some of the things. We put 3 principles, 6 arguments that you would need to do. But most particularly, and one of the things that John always asks me to stress is, there are 3 things that we put into an equation to try and work out, which is the one at the bottom there. So the first of those is, there is a residual risk that the state is prepared to hold, that it all goes horribly wrong, because ultimately that'll be theirs. There's a bit that I can insure, but our job as engineers is to do the rest of it. And I'm pretty sure that the state and the insurance industry between them do not intend to hold a 50% probability of failure or a catastrophic thing that shuts down the entire food supply system or any of these sorts of things. And that is what we need to consider when we get to that. So our engineering task is to actually get to a point when we do security by design that we can actually do that sort of stuff. So these are my sort of takeaways and observations in relation to that. For driverless cars, I realise we don't have driverless cars. But what I'd like you to invite you to consider on that one is every time you press your ABS and it goes and takes over from you, that includes all of the characteristics of a driverless car. It took over from me, it's steering, it's braking, it's accelerating, it's got the high-speed emergency braking put into that, and 15 seconds later it gives it back to me if I'm lucky. Every bit that you think you might want to in a driverless car is already present. It's got AI in its systems, machine learning, it's got distributed components. So take that as your working thing and work on that kind of stuff and figure out whether we know how to do brakes. Because I'll argue that we're still doing the way we did in the 1960s, not in the way that... And there are so many benefits we get out of this that we owe it to society to get that sorted. Anyway, for driverless cars, we don't currently or foreseeably have engineering or scientific practices to guarantee to any legally satisfactory level the behaviour of the autonomous systems. And you were talking about that. That is deep tech, that's what we need to talk about. That's what security by design means. It means I know what is the basis on which I am saying things, not just because I learnt it at school or whatever those things. And we as engineers have only just begun to factor in the huge degree to which we're dependent on human diversity. So think about this. You know, when you go to a junction, when you drive cars, what actually keeps us from a catastrophic failure is that everybody behaves differently. Our risk is we're designing things so that everything behaves the same. So we are designing our very own COVID, only much more catastrophic. It should take about 5 days, I think, to transmit around the world. Cyber techniques that cannot scale, and this is a really important thing. You've got to be able to scale. You've talked about power, you've talked about AI. We have to get cyber techniques into this stuff that can scale. So if you've got somebody telling you that I can do penetration testing on 10 devices, ask them how it scales to 250,000 safety critical devices over an 8-year period of time. And cyber resilience is designed to take advantage of what we know using tools and techniques. We must do that. And it's these tools. And that's part of what we do here. Working out how to put this stuff into tools, how to use data science, how to put this data that we have, not to go, oh, I can do more penetration tests, because that doesn't scale, but to actually understanding in real time the designs of our systems and how they work. And that is what we've been working on in relation to security by design. And I think if we can get it, the really significant thing about that is that means that we are managing for the first time as a security process emergent properties. So we are right in the sweet spot of where people generate value instead of right in the sweet spot of where they get cost. I was nowhere near, was I?